So at the end of Organic Chem 1, what we did was end it with substitution and elimination reaction. So substitution reaction, we took an alkyl halide, turned it into something else. Elimination, we took an alkyl halide and turned it into an alkene. Now, we're going to take alkenes and turn them back into some sort of single bonded alkane with some functional groups on it, which is known as an addition reaction. So an elimination reaction, you literally eliminated something from the alkyl chain, and in an addition reaction, we're going to add something back. This is the general mechanism for an elimination reaction. Okay, so we're talking mechanisms again and things like that. So we've got to be able to draw mechanisms out. A lot of the exams this half are not going to be multiple choice. They're going to be the type where I give you something, you need to work it out and get it back to me. Okay, so what do we got going on here? All right, in an elimination reaction, we have an electron-rich pi bond right here. Okay, so you have an alkane, or you can have an alkyne. Okay, so you have an alkene or an alkyne, and we're going to turn it into an alkane. So an alkene or an alkyne is going to turn into an alkane eventually. So you have an electron-rich pi bond sitting here in your alkene, and it's going to attack an electrophile. An electrophile will have a positive charge, or it'll be missing a lone pair of electrons. Okay. Opposite of a nucleophile, which is looking for, again, positives. An electrophile loves negative things, wants negative things, wants these pi electrons. So the pi electrons attack the electrophile. The electrophile attaches to the carbon. Now, here's the deal with attaching to the carbon, and I alluded to this at the end of Orgo 1, but I'll review it again. I am going to make the carbocation that is the most stable. So my electrophile will attach to the carbon that would not give me the best best carbocation. We'll talk about that. It's known as Markovnikov's rule, where the electrophile will attach to the more hydrogen substituted carbon, leaving the more alkyl substituted carbon to make the carbocation. Once this happens, this carbocation is not stable, as we talked about in Orgo 1. I would rather have a lone pair. I'd rather be a radical than I would be short all my electrons with that positive. But what that positive will allow is some sort of nucleophile now to come in and attack via the second half of an SN1 reaction. Okay. So that is the general mechanism. First step, break the double bond. Second step, whatever nucleophile is what we're looking to add, will attach. So we're really adding in an addition reaction two things. An electrophile initially and a nucleophile second. What could my electrophile be? How about a proton? That simple. An H plus could be my electrophile. Okay? Doesn't have to be overcomplicated. All right, so let's look at, essentially, we're going to look at different addition reactions and their mechanisms. Okay? So hydrohalogenation is the addition of a halogen across the double bond. Actually, hydrohalogenation is a method, okay, or I should say just halogenation in general without the hydro, is a method that can be used to detect alkenes. One of the ones you can use, and we'll talk about this in a little bit, is you could take an alkene, you add bromine to it, or bromine water, all right, and bromine water is going to be brown, and if there's a double bond present in the right conditions, the bromine will add across the double bond and the brown color will be gone. In our case here, we've got a hydrohalogenation. So we've got hydrochloric acid, hydrobromic acid, hydrofluoric, hydroiodic. Usually, because of reaction rates and timing, we're going to use Cl or Br. Okay, and I know that these are capitalized and they shouldn't be, but again, these are openware PowerPoints that I'm using. So, all right, so what happens? I've got a double bonded electron-rich area of pi electrons. They are going to attack. Now, we have to remember that this is a polar covalent bond, so hydrogen is partially positive due to the electronegativity, and chlorine is partially negative due to its electronegativity. The very pi-rich area is going to attack the partial positive. That's key, because my electron-rich area in an addition reaction, electrophilic addition reaction, is going to look for something positive. So I need that polar covalent bond there. Now the question is, okay, the hydrogen's going to add. Is it going to add to carbon 1 or carbon 2? Well, it's going to add to carbon 1 to give the more stable carbocation. This is the only product I can get this way. I cannot get 1-chloropropane. I cannot get this, essentially. Whoop. As I was writing, double-clicking there. I can't get this. Okay, this cannot happen. 1-chloropropane cannot happen, because my hydrogen is going to add to the more hydrogen substituted carbon in our double bond. Carbocation forms. Nucleophile is now left over because it was created by the removal of the hydrogen. Electrons went to chlorine. Chlorine gets the minus charge because of these electrons. Now chlorine is free to attack the carbocation, and we end up with, again, 2-chloropropane. So that is, again, following the general mechanism, but this is known as hydrohalogenation. So when I was studying this, and what I suggest you do is, make yourself some notes. What's going to happen? How's it going to happen? Given, okay, here's my, reactant, here's my reagent, here's the product I should get. Because there's going to be a bunch. So that leads us, like I said, to Markovnikov's rule, also known as Markey's rule. And it's essentially in reactions with alkenes, okay, a hydrogen will add to the carbon with more hydrogens, and the halogen will bond to the carbon with fewer hydrogens. And if you want to make it more general, my electrophile will add to the more hydrogen substituted carbon to make the more stable carbocation, and my anion or nucleophile will attack the carbocation. And anytime, I know no one is logged in or whatever, but anytime you have any questions, just type in the chat. I don't know if this is a review for some of you who had Orgo 1 without me, but if it is, good for you. If not, let's keep it going here. Somebody that had a repeating Chem 1 or Orgo 1 might have got to this. This is where I like to pick up with Orgo 2. All right. So, again, stability of the carbocation. Remember, a tertiary is more stable than a secondary, and a secondary is more stable than a primary. Okay. In something that's symmetrical like this here, which is 2-butene, it doesn't matter which one becomes the carbocation, because they're both the same. As long as I don't have this or this become, all right, the carbocation. So if this left one became the carbocation, that's fine. The right one could also become the carbocation. Okay. So we're looking really, after you make your carbocation, make sure you made the more stable carbocation. Okay. Possible, the most stable possible. So again, like I said at the beginning, we can't get 1-chloropropane from our reaction. Our main product's going to be 2-chloropropane. We don't really want that primary. And here's what'll happen. And we talked about this in the last, in Orgo 1 at the end, and I kind of threw it on you and said it's going to come back. Well, a week later it's back. But let's say we did do this. Okay? This broke down. The hydrogen went here. Okay? And we had this as our carbocation. All right? We had this waiting. Let's just imagine this happened. Even though that's not the stable, even though that's not the possible, this is the intermediate in between here. Before chlorine goes to add. What's going to happen before chlorine adds? Do we remember what we talked about? Do you remember what we talked about that's going to happen? That I can't even if this somehow happened. All right. Even if this somehow happened, do we know why it won't really happen? Well, the reason it'll happen is because of the hydride shift. This would actually move right over here so that we couldn't get this non-stable carbocation, that we would end up with the more stable carbocation here. And even if somehow that happened, we'd get that hydride shift. This should have been 2 here. CH2, it'll be a CH3 now, and the chlorine would still end up attacking here and end up over there. So there is no method this way of creating a alkyl halide that is a primary alkyl halide. So when you create your carbocation, make sure you create your most stable. Then look and make sure you can't do a hydride or even a methyl shift, where I could shift the whole entire methyl group over, which could happen. Okay. So again, they're showing stability and what side we would go to and things like that. And check it out. They're showing the hydride shift right here on this slide. All right, so the hydrogen should go to this carbon. It did. I have this here. It's a secondary. So this is a secondary alkyl, or a carbocation. I was going to say alkyl cation, but a carbocation we'll go with. But, and this is what's crazy about Orgo or atoms in general. The atom just knows. The molecule just knows. I can move this and just be more stable. So it shifts it over here, and we end up with a tertiary. And instead of being, 1, 2, 2 bromo this way, it's actually going to be 2 bromo that way with my methyl groups on it. Okay. So this is again known as a hydride shift. We can also shift an entire methyl group. If this was a CH3 group, this whole CH3 group might drop here. And that would be known as a methyl shift. So look for that when you create your carbocations. Okay. How about alkynes then? I said alkynes can do these things. Okay. Well, let's talk about alkynes. All right, alkynes with an alkyl halide. An alkyne with an alkyl halide, 1 mole ratio to 1 mole ratio, is going to essentially give us an alkene with a halogen attached. Okay. So one of these pi electrons is going to attack that hydrogen, which in turn is going to kick off here. All right, which in turn is going to come back and bond to one of these. Okay, whichever one's going to give me the more stable carbocation. And we're going to end up with an alkene. However, if I use excess, or they might say double, or 2x, the alkyl halide. This will attack here once. This will attach. Then this will attack again, the second dose. And this will attach. Now notice something in here. It attaches to the same carbon. That is key. Markovnikov's rule is followed. Markey's rule still stands. Essentially, you start with this product and add another HX. Well, the hydrogen's going to go to the more hydrosubstituted, that one right here, which means my halogen is going to end up there. And again, I'm showing it all in one step, but we saw it happens in multiple steps. Okay. The term that we create from an excess, or not an excess, an alkene with a halogen on it. So when we create that from our alkyne, that's known as a vinyl halide. A vinyl halide is an alkene that has at least one halide substitution. So if you see a compound that looks like an alkyl halide but is an alkene, so it's not an alkyl halide, this is known as a vinyl. Okay. So the product of one-to-one relationship of an alkyne with an alkyl halide will give you a vinyl halide. So this would be known as vinyl chloride, as you could see it below. Reactivity order. HI, very fast to react, usually not used in a lab. HF, really slow because fluorine is so electronegative, pulling that hydrogen, it really doesn't want to let it go. Makes it a little bit tougher. So again, to do these, we usually do HBr and HCl. We are regioselective. Okay, which means that my halogen is going to attach to a specific carbon. The hydrogen is going to attach to a specific carbon due to Markey's rule. Our reactions proceed via protonation, all right, to give the more stable carbocation intermediate. Okay, and we're dealing with a planar, so we don't have to worry about stereochemistry, R and S, and all of that. Okay, we talked about vinyls. And if we treat it with excess, we're going to go all the way to, like I said, an alkyl halide that is di-substituted on the same carbon. All right, so that's alkyl halides. That is making halogens. Now let's talk about making alcohols. Okay. If I take an alkene and I add it to an acid, an aqueous acid, the acid of choice is usually sulfuric acid in this case, we will make an alcohol. So, alkene, if we were keeping a table, with an acid, specifically H2SO4, we're going to create an alcohol. Markovnikov's rule still exists. And we don't have to worry about stereochemistry. But the carbocation intermediate, you have to look for hydrogen and methyl shifts. So if we take a look at the general reaction of what occurs, H2SO4 brings the hydrogen to the party. In reality, and sometimes I have to point this out, this H plus isn't coming from the H2SO4. It is, but it's not attached to the SO4. Since I'm in water, this is really hydronium. Okay? The SO4 is hanging out over here, doing its thing, waiting to get established at the end, because that's what happens. We recycle it. Okay. Once that hydrogen attaches and gives us the carbocation, this becomes essentially water. This water is now free to attack our carbon. The water attacks the carbon. Water doesn't like to have 3 bonds, so my hydrogen leaves by my base. Well, where's my base come from? I can add a base. Possibly the SO4 2- could be that base. Takes off one of the hydrogens, and I'm left with an alcohol. Key here again, due to Markey's rule, I'm either going to be a secondary or tertiary alcohol. I cannot be a primary alcohol this way. So over the arrow, you may see H2SO4 in the reaction. You may just see H+. Know that when you see this, or the full-blown acid form, or the word just acid, remember that you are going to make an alcohol. Okay? Again, anytime I'm going too fast or you have a question, let me know. All right, what happens in the presence of an acid with an alkyne? Okay. With an alkyne, we make an alcohol with an OH group on it, and what we call that is an enol. Okay, if we do this with an alkyne, we make an enol. And our enol could be readily turned into, right here, a ketone. As long as we're bonded, as long as we're not ethine that we're starting with. Okay. So my products of water with an alkyne is going to be an enol, which can turn into a ketone. Okay. And here's the exact mechanism. This one, it's basically the same thing. We create our enol, but then I'm still pi electron rich down here, so nothing stopping attacking another hydrogen or so. And that's how I could turn into a ketone. Okay. And it's not like it's stopped. We'd have to actually stop our enols and pull them out, because in that environment, we're going to turn to ketones very quickly. Okay. Again, Markey's rule is going to predict everything. So we're going to follow Markey's rule. Now, that's not always the case. There is a reaction where we won't follow Markey's rule, or we won't need to, and we'll talk about those. All right. Halogenation. The addition of I2, Br2, or Cl2, and again, based on reaction times, we usually focus on Br2 and Cl2 being the reactions. Here's the deal with it. What's the difference between this compound right here and our alkyl halide? And the difference is There is no partial positive charge. There is nothing that our pi electrons want to attack on that. So what happens? How does this reaction even occur? Well, the first thing I want to point out before we even do that is, and it says it right here, anti, our halogens add on opposite sides. That's important. And you'll see why, because of the method of it adding. Okay. Usually dichloromethane, which is this right here, also known as methylene chloride, is used in this reaction because we don't want a reactive polar solvent. We want something that's inert. We are stereoselective for the first time. We have to add in that anti position. But we create this crazy halonium ion as our intermediate. So here's our carbons of the double bond. And what it does, okay, is actually forces its way in to grab one of those bromines and kick electrons over here. So our intermediate is this halonium ion, which essentially, if we draw it out just so you could see it, looks like this. Okay. Now that Br is making too many bonds, it's going to have a plus charge. What then happens is that the negative attacks the bottom, and as we see here. And the reason it attacks the bottom is steric hindrance. It can't get through up here. So it attacks the bottom, which causes this bond to break. Giving the electrons back, and ending with, as you can see over there, something that looks like this. Okay. So our first time going through addition reactions where we actually have a stereoselective product that we have to look at. If you draw this on the same side, it's not correct because that's not the process. Okay. All right. The more alkyl substitute the carbons in the double bond, the faster the rate of the reaction. Okay. How about if I have a halogen, all right, but water is present. This is why we don't use water. This is why if you're doing a halogenation in a lab setting at some point in time, you have to make sure your glassware is completely dry. You go and wash your glassware before doing the experiment and it has water in it, you're not going to get your anti-halogens across the double bond. What'll happen is one of your halogens will attach, but then the OH from water ends up being a better nucleophile than the halogen itself, and will bond and beat the second halogen to the punch. Okay. So if water is present with the halogen, you're still going to get the anti, but instead of two halogens, you're going to get a halogen and an OH in the anti position. Okay. Clean glassware, but dry glassware is important. Okay. So the bromine attaches, like I said, but the water beats the bromine to the punch, and essentially the bromine goes off with the hydrogen from water. If we continue to put water in and 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 over-contaminate it with water, we end up with an epoxy. Okay. That's just a little side note. And we'll get back to epoxides and all of that stuff when we talk about ethers and all of that, but realize over-contamination could end up with epoxies. All right, and you definitely don't want that if that's not what you're looking for in a lab. Okay. So let's say we take our ethylene chloride, or ethylene, and we add chlorine and we make dichloroethane, like we have here. Okay. If we heat it, we can actually make a double bond reappear and turn our product into a vinyl chloride. So not only when I'm doing my reactions, I got to make sure water contamination doesn't play a role. I also have to make sure heat doesn't play a role, because I'm setting out to make 1,2-dichloroethane, but I have too high of a temperature and I end up with a vinyl chloride. Okay. So these are just little tidbits of things that could go wrong if we're not watching. So let's look at this one. Oxymercuration, demercuration of alkenes. Now, I don't know of an institution that is still actively using mercury in their labs. Mercury is a safety hazard. THF isn't the greatest thing in the world to work with. All right, but if we did treat it with these two steps, it's another way to create an alcohol. Okay. OAC is standing for acetic acid, or acetate specifically here. Okay, so mercuric acetate with THF and water, and then treat it with sodium borohydride. Could end up giving you an alcohol. It is a way of getting an alcohol, but it is highly toxic and really not preferred. But again, you may see this on a worksheet on Blackboard, or if you're using online, looking up reactions, you may see these pop up. Okay, so you should know what happens. The sodium borohydrate's there to get rid of the mercury. All right. Again, regioselective because of Markey's rule. We're going to make the most substituted alcohol. We form a cyclic mercury ion during the process. I never did this reaction. Okay, and I was taking organic in, 20 years ago. And I never did this reaction in a lab setting. All right, so I would probably guess the 60s was the last time, 70s. Schools aren't going to really allow large amounts of mercury on campus when not needed. Okay. So am I going to ask you the mechanism on this? No, I'm not going to ask you for the mechanism on this one, but you should know what product you get if you use mercury acetate. Okay. What if I don't use water? Instead, I have the mercury acetate in alcohol. Well, if that's the case, then I can contain an ether. Why would I want to do that? I don't know. Maybe you want to make an ether. But here we go. Couple problems. Number one, mercury, toxic. Number two, ethers, depending on the ether. But ethers are usually flammable. So you want to make sure that you are in not this, but water if you were doing this. But if you were doing this reaction, you could also create an ether if you used an alcohol. So if you use the alcohol, you're going to create the ether. But if you don't want to create an ether, make sure you're using water. Okay. So we take a toxic reactant or reagent and make a flammable toxic product out of it. And here comes the most famous addition reaction out there, I would say. It was so famous and so great that Herbert Brown won the Nobel Prize for this reaction. It's a reaction of an alkene, okay, with BH3, THF, all right, in the presence of hydrogen peroxide. It was invented by Herbert Braun, hence that's why he won the Nobel Prize in Chemistry in 1979. So what's so great about it? All right, first of all, borane is electron deficient, so therefore it can accept electrons. So therefore it acts like a Lewis acid. Okay. So BH3 is going to be attacked by my electrons. But that's not the fun part. I am going to create an alcohol. That's important. And here they're showing borane attach. And the other beauty of this is since there's 3 hydrogens, boron could attach to 3 different double bonds. And I'll show you that in a different slide. Okay. Like this right here. But I didn't get to the good part yet. So what? It does that. Great. Woohoo. The thing is this right here. The big woohoo about this reaction is that it adds in anti-Markey ways. Instead of my nucleophile ending up on my most alkyl substituted carbon, it actually ends up to getting added to the carbon with the most hydrogens. Okay. It gets added to the carbon with the most hydrogens. That's a big deal because now what this allows us to do is make primary alcohols. The old way with H2SO4, even with mercuric oxide, I would have to make a secondary or tertiary because Markey's rule stands in place and I got to make the most stable carbocation. But the way boron bonds and the way boron interacts with the alkene chain allows the OH to add in the primary position or to the carbon with the most hydrogens. So please take a note on that, or note that this slide is important, or whatever it is you need to do. So the product where you would think the OH would attack here, because that would be the best carbocation, the OH actually attaches there. Very important, because now you could create a primary alcohol. So we could see why this was important. It found a lot of things. We're making coordinate covalent bonds. The carbon is giving both electrons to boron to bond because hydrogen's going to take one as it leaves. But that blocking up allows for a primary addition. Okay. It happens in the syn form, so they're in the same side, not in the anti form. And here is the breakdown. You can see how it's blocked up, why the carbocation doesn't form, when the hydrogen leaves. The boron's here to leave later, and that's how we end up with the primary. I am not going to ask you the mechanism on this one. You should take a look at it. Again, it's very high energy, this intermediate. However, I do need you to know that this goes anti-Markey. All right, we'll continue on here. A carbene. A carbene is a carbon that's not only short a bond, but also has a lone pair on it. Okay, so as you can see, this carbene here is only making 2 bonds with a lone pair, so it's short electrons. They kind of call, again, as it says up there, carbenes are known as half alkenes, or half of an alkene. Okay. If a carbene attacks or gets attacked by a double bond, a pi bond, it'll make a cyclic structure. It'll make a 3-carbon ring cyclic structure with whatever my tails are coming off of the carbene. Every time I'm going to have some sort of cyclopropane something. Okay. So those are carbenes. Okay. That shows you the formation of them and using them to make bonds. So this one's a chlorocarbene. All right, we're going to attack, lose one of the CLs, but we're still going to make that ring structure. You can make it a ring on a ring like it shows here, or we can make a ring, okay, on a straight line or non-ringed structure. So again, see a carbene, make a ring. Carbene ring. Here's a reaction known as a Simmons-Smith reaction, okay, which is very similar to adding a carbene. There is a prep phase in the process to create it, but we still get the same product. A ring structure with the carbene. The thing that separates it is Simmons-Smith is a specific way of creating a carbene. That's it. You probably won't do one of these unless you're in an advanced organic because of ether. I know a lot of places are getting even rid of using ether anymore because you don't use a lot of it and the shelf life is very, very low. That being said, if you ever have to use ether, a couple things before you even touch the bottle or handle it and shake it. Move it around it should be in an explosive refrigerator. Take a look at the date. If it's more than a year old and it's been open, even if it hasn't been open, you really shouldn't be using it. Number 2, before you even touch the bottle, if there's white crusty stuff on the top of it, okay, and that goes for pretty much any organic substance, all right, but if your instructor says, oh, go in there and grab the ether, and you see it has white crusty stuff on it, do not touch it. All right, head to your professor, whoever, your PI or whatever it is, and inform them because that ether is oxidized and is equivalent to a bomb. All right, so getting rid of ether, all right, at the right time. That's why every bottle should be labeled when it was accepted, when it was opened, all of that, so that you know. Okay. So ether goes through a process where you're going to essentially go from something that's flammable to something that could possibly be a bomb. And just the slightest movement could set it off. So that's why I'm saying if you see white crusty stuff on a bottle, inform somebody before even touching the bottle. But usually ether, like I said, is used in small amounts anymore, if at all. I know places are getting around not using it. Epoxides again could form if we can use oxygen instead of a carbene and do the same exact thing and get that ring structure and form an epoxide. So we have different ways of forming an epoxide. We can do it with an O with a lone pair on it to get across, or we can do it, like I said, over contamination with water. All right. We don't need to do them. Okay, let's get to this one. An addition reaction using osmium tetraoxide. Okay, probably never going to use osmium. There's another way, a cheaper way, and a more efficient way to doing this. But here's how it adds. Okay, so the structure of osmium tetraoxide is osmium double bonded to an oxygen, double bonded, and these oxygens looking for something to bond to. All right, so that's what happens. They add across the double bond together, so there's no worry about Markey's rule or anything here. And we create what is known as a diol, a double alcohol. Now the thing about it is, osmium is very expensive, reacts very, very fast. Okay, and this is my favorite part about organic chemistry. We're X amount of years, it's 2020, and It reacts fast with the ether and forms this black precipitate. It's thought that the black precipitate is the osmium diester, that kind of double linkage before it breaks apart. It's thought to be that. Okay. It happens so fast that they don't measure it or haven't measured it, but that's what they think that it is. It both adds on the syn side, or if you want to say on the cis side, but the double bond isn't there anymore, so syn diol. But the thing is, osmium tetraoxide is ridiculously expensive and could be toxic. Not could be, is toxic. So what do we use instead? Something cheaper that we used in Gen Chem. We can get the same results using potassium permanganate, sodium permanganate, anything to get permanganate into the reaction. So if you're using permanganate or the osmium tetroxide, you should get a diol out every time. They should be on the same side. Like so. This one here, safer. I don't know what kind of F that is. And a lot cheaper. Okay. And get the same result. How about ozone? Now look at this. Look at what ozone can do. Okay. Ozone is crazy. Ozone is a very strong oxidizer. Ozone is 3 oxygens bonded together. We talked about ozone in resonance, but let's look at it again. Here's what ozone looks like. All right, ozone, ozone, like so. Creates these intermediates. I'm not worried about the mechanism. Why does that O flip in between there? There's some ideas. But here's the importance. Wherever the double bond is, we get a split. We get a fracture. Okay. And we create 2 carbonyl carbons. So we create 2 carbonyl carbons. And as you can see, here's our double bond. Here's where our split's going to be. We create hexanone, and we create acetone. Acetone here, and cyclohexanone there. Here's our split. What are we going to create? An aldehyde, and since we're going to put a double bond O here and have a double bond OO over here, we create a ester. So what we're going to create is carbonyl carbons. The products we could create, in theory, okay, depending on what we're attached to, is anything with a carbonyl carbon. A ketone, an aldehyde, an ester. The only thing you won't be able to create per se is a carboxylic acid. Unless, of course, this was bonded instead of to an H, an OH. Then I guess in theory, you could create a carboxylic acid. Okay. Again, I'm more interested in, do you know the products? Do you know the general mechanism? Do you understand what's going on? And do you know what products you can get? Easiest one, in my opinion, is this one right here. Take an alkene, add hydrogen gas to it with some metal catalyst, palladium, platinum, or nickel, and get out an alkane. Do it with an alkyne. Do it with a 1-to-1 mole ratio, get an alkene. Do it with excess, get an alkane all the way down. What we're doing here, in terms of things, we are reducing our alkene and turning it into an alkane. The catalyst is needed because the hydrogen bonds to the catalyst first to make it prepared for the double bond to want to attack a partially positive something, because just like Cl2, Br2, H2 is nonpolar. Okay. And it doesn't matter if I'm in the cis form, trans form, whatever form I'm in, it's going to work. I'm going to end up with the same thing every time. So I've got one butene up top. I've got trans 2-butene. I've got cis 2-butene. They all end up being butane at the end. Again, this is the mechanism if you're really interested in that. But those of you going on for a career in organic or biochem, you'll take a mechanistic organic chemistry course, or they might call it Orgo 3, where all you do is talk about mechanisms over and over. Okay. So what if I have two double bonds? Okay. There's three different ways I can look at double bonds if I have multiple. Okay. I'm going to show you the three ways. All right. Let's use a 6-carbon chain. 1, 2, 3, 4, 5, and 6. Okay, 1, 2, 3, 4, 5, 6. I could be here and here. All right, 6. I could be here and here. So this is 1, 5 hexadiene. This is 2, 4 hexadiene. Or I could be, let me get a little bit lower here, right next to each other, multiple different ways. 3, 4, 5, 6, let's say here and here. Okay. All right. Where my double bonds are located to each other, they have different names. If they're separated by more than one carbon or more, they're known as isolated. If they're separated by just one carbon, they're known as conjugated. And if they're right next to each other, they're known as cumulated. Okay. I guess for my OCD, I should spell it all out, right? So my double bonds, if I have a diene. Now, what if I have a diene and I want to do one of those reactions? Okay, that we're looking at. Well, guess what? The pi bonds don't care. Both of them will attack the hydrogen or the bromine or whatever our reactant is. But back to looking at these, the isolated, the conjugated, and the cumulated, which one is the most stable? And the most stable is the conjugated. A conjugated system means alternating double bonds. Why is that more stable? The reason a conjugated system is more stable is because I could have more resonance. And the more resonance I have, the more stable I am. Here they're talking about our differences in hybridization with these. But again, like I said, the more resonance I can have, the better. Right? If I look at isolated, go back to our webcam here. If I look at isolated and I bring this here and this here, I go to a conjugated system, and it's really not the same energy, and I guess we could say it's resonance, but is it really? Here, I could go here with here. That's one way. I can go here and here. That's another way. Down here, I'm pretty much stuck. These two are repelling each other so much. Yeah, I can move this here and then that there, I guess. But them being so close to each other, it's not the best thing, and just keep moving them down. And yes, they'll have about the same number of resonance, but having those double bonds close to each other, really not good for stability. So our conjugated diene, the way it sits, has less energy because they're spread apart. They're not spread apart as far, and they have more resonance. So they're better than the isolated because they have more resonance, and they're better than the cumulative or cumulated because they're stuck, not stuck next to each other, repelling each other greatly. Okay. So like I said, a conjugated, more delocalization, more resonance. Isolated, and this is all they're going to keep saying. They're going to keep telling you what I just said in multiple slides here. Okay. All right. How about acidity of our alkynes? Alkynes could create carbanions if they want in the presence of a base. Alkynes in the presence of a base could create a carbanion, which could be used as a nucleophile later on. Put that in your back pocket. Alkynes are more acidic than alkenes, which are more acidic than alkanes. And it's just because this hydrogen, and essentially, all right, we know that that pull of those electrons, that inductive effect, is going to make that hydrogen easier to pluck. That's why it says it's just looser, I guess. Well, it is because of the electron richness downstream here. Okay. All right, so that ends addition reactions.